See, if I was just looking at the notes yesterday with somebody's copy, there leads to some small thing. If you go back to your notes, is that what we said or we said something else? Did we say it this way? Right? No confusion about it? Because obviously, but this is not correct. This is not correct. Do you think this is correct? This is not correct because for this to be correct, there has to be inversion here, dispersion permitted here, and again does this make more sense? Right? This makes more sense. I just scanning somebody's this thing. So you see here, since this is inversion, no dispersion can take place here. There is again elevated inversion, so there is no dispersion that can take place here. Okay. Here you see either the conditions are neutral or unstable. So in that thing which is a little layer which is left, okay, that's where the dispersion will take place. So for the trapping, the atmospheric conditions in terms of the temperature and the height would have an elevated layer on top and ground based inversion. Inversion on top and inversion at the bottom. Is that clear now? We were discussing about the modeling part because we have understood, we have studied at least to a small extent what is meteorology and what is atmospheric phenomena and things like that. So what we will do is that I will kind of do it again about the box model. You have a box, okay, and the wind may be blowing like this and it is going like this, okay, and this I am calling this as delta x, this as delta y, and this I am calling this as z. And delta y, I assume this to be unity because I can have many boxes, and if things are similar, so the condition across, okay, or in the crosswind direction, this is the wind direction, in the crosswind direction it will always be the same. Okay. And we said there were some emissions that might take place inside the box, okay, and that we call that as QA, okay. And the wind which is blowing it in the box, which may be a part of city, or that can be city, or your city you can divide in many boxes, okay. So here is the initial concentration, the concentration outside the box is, let us say, C naught, and wind speed is u. Okay. Then we want to find out the concentration inside the box, which may be typically your city. So to find out this, what we said was accumulation in the box, okay, equals to input to the box minus output from box. In units, since we are doing the mass balance, it should be always be mass per time, mass per time, mass per time. Okay. So accumulation, I can write this as, I'll directly write in differential form, del C by del T. Okay, I have to get the units to mass per time. So what do I multiply here? The volume of the box, right? We are inside the box. Okay, so y times z equals to the input to the box. One is this input. Okay, so this will be concentration C naught times the area, the cross sectional area, okay, that is y times z or delta y times z, okay, times wind speed. Okay, what else is the input? QA, and let me define QA equals to mass emission of whatever the pollutant is per unit area per unit time. Okay, so QA, what do I do? Multiply by the surface area of the box. So that is delta x times delta y. Okay, and output. Okay, and I am assuming the box to be completely mixed reactor. So what do I do? Minus, okay, and suppose the final concentration in the box is C, okay, and box you are modeling as CFMR, completely mixed flow reactor. Okay, so then what I can do is C times delta y z times u. Okay, this is what is I can write. Okay, what do I do if I say that the pollutant inside the box is somehow decaying or reacting with time? Okay, that's possible because some pollutants within this box can undergo some kind of transformation or change. Okay, so what thing I need to add here? Okay, what we'll do is that we'll do this analysis first, and we can also add another term where there is some decay of the pollutant is going on. Okay, so if you let's do it this one for the time being. So if you simplify this and put at steady state close to 0. Okay, if you can give me the expression and I put delta y equals to 1, then the expression which we drove yesterday was C naught, okay, plus QA delta x times uz. Is that what we got last time? Right? Things look simple, but it has a lot of applications. Okay. So whole city you can divide in grids. This I am making the plan of the city. Okay. And suppose the wind is blowing like this. QA may vary from QA1, QA2 and so on and so forth. Okay. Then, and wind is blowing. Okay. So whatever is the concentration C, that becomes C naught for the next block, right? And that way you can solve it continuously, the concentration here, 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 here. Okay. Before we make some example and things like that, suppose the same pollutant was decaying in the box. Okay. It means the output is just not only because of the wind that is kind of cleaning the box, but there is a decay, and the rate constant for decay is, let's say, K. Okay. You have done that before. That is a decay rate constant for that pollutant, whatever that pollutant is. So it means concentration will decrease. Okay. What do I write if decay constant is K? Kc. All right. Kc. Is that all? Times delta V. What is delta V? Kc. Okay. What do I write? Volume. Correct. See, I am saying this thing is decaying. Okay. So you have minus Kc, we have to get the same dimension, mass per unit time. And K has a units, that is decay constant is always time inverse, right? So C by T in a way, okay. So I must multiply this with volume, right? Is that everyone agrees with me, right? So we are also considering the decay of the pollutants. So I can say delta X times delta V times Z. Okay. This is the decay term. And you can still simplify the equation and you will get some answer. Okay. We did, I'll do a very simple example which was kind of a realistic thing which we had. It was estimated that QA of SO2, okay, in Kanpur was of the order of, let's say, 200 tons per day. Okay, and this was the total in the city. So you divide the city area, let's say, by 10 by 10. So that comes out to be 200. Okay, that's kg. Okay, kilometer per square. When with simple this thing, when the concentration was estimated, okay, that concentration came out to be much less than what was the measured concentration. Okay, if you want, we can do this calculation quickly. Okay, just help me doing this calculation. So this is kilometer squares, don't forget. So that's what I can say, 200, 2000, and then with kilometer meter square to the 10 to the power minus 6. This is kg per meter square, or I can say 200. So kg I can convert into grams. So that will be 10 to the minus 3 milligram, 10 to the minus 6 gone. So much milligrams per meter square, or Okay, let's do it in milligrams. Okay, 2000 milligrams per meter square per day. Okay, and suppose this is the emission that we are talking about. Okay, let's also do this one in terms of seconds. 200,000 milligrams per meter square. And this I have the calculator, so I'll do that. 2000 divided by 3600. I want to get in, oh yes, there has to be 24 too. That what, suppose this is the number, and wind speed was, let's say, 4 meters, that's average wind speed, and alright. So suppose that then I can simply find out C. Suppose initial concentration outside Kanpur, I assume that to be 0. So the QA is 0.023 times the delta X. That is the length of the city I can take, alright. That is equals to that many meters divided by 4 meters per second divided by the mixing height. I can take that as the 1000 meter, that is typical that we discuss. So Z equals to 1000. Okay, so this gives you how much? This goes off, and this will be 2.5. So I'll give you the exact number. Okay, so in terms of microgram per meter cube, this will be 57. So you expect average concentration of sulfur dioxide in Kanpur to be about 57.5 microns per meter cube. Okay, is this part clear? Okay, see, the idea is not simply doing the calculation part. Okay, you always deal with the actual things as a field engineer. You should make some sense out of it. Then we compared this number with the measurements which was done in Kanpur for several years, and we found that average concentration which was measured in Kanpur at some 5 different locations was always around, it varied between 15 to 25. Okay. So then it suppose the actual concentration of 15 to 25. So what it would say is either this number is incorrect, okay, either this number is incorrect, or what could have gone wrong, and then we checked this number over and over again, compared with various cities, and we thought this number was very good. So we are almost getting just the half of this one. We are talking very broad estimates. We are not done any kind of sophisticated modeling, nor we are talking about great deal of numerical models and using the computers and things like that. So if this was 57.5, and I am telling you the real example, and what the measured values were like 15, 20, 15, 20 for many years, okay, then obviously what we thought, okay, immediately you think maybe the measurements of sulfur dioxide is not correct, because mathematics is probably all right. Okay. So then we checked the methods and things like that. The methods were all right and things like that. Then we thought that what could possibly go is that maybe this thing is happening. Okay. Then one of the research was done here, and then we said, well, along with sulfur dioxide, what can happen to sulfur dioxide with your atmospheric chemistry? What will happen to sulfur dioxide? Go into sulfates. That is the first primary reaction. So then along with this one, sulfate measurements were done, and then the sulfate measurements were almost twice the value of sulfur dioxide. Again I am talking the broad scale, not very fine scale. So that told us that, well, there is something else happening, and one of the reasons of not getting the sulfur dioxide, the average levels, okay, we are not talking about specific, we are not talking about a particular day, but we said, well, there was something wrong, and then we found this particular thing was important, and then that is how we found out the sulfate levels were higher, and in fact at most of the places in northern India, sulfur dioxide is very quickly converted into sulfates, okay, whatever the reactions and things are. So you apply this thing, okay. The other application can be, okay, suppose the reaction was not important, then you can say, okay, this is not properly done, or you can also find out, suppose if this was higher, okay, and this term was giving lower, it means the pollution is coming from outside. Simple application. You should always think not getting the numbers and doing things as to how you can apply at the broad level, and at least you know the broad picture, and then you can go to the finer details slowly. Here we have not considered any turbulence, anything, it's just completely mixed flow reactor. Okay, let's slightly go into some specific thing now. I want to talk to you about flux, pollutant flux, because this we are going to use a lot. Okay. So how do we define the flux? Suppose there is a chimney, I am just giving an example, and the pollutants are traveling. Okay. So if I have a, let us say, a block, not only block, let us say I have a strip. Okay. And the point here is, let us say, x, y and z. Okay. So J, if I have to define the flux, okay, this is nothing but mass of the pollutant per unit area, that is the area, time. Okay. Now the one thing we want to define, the another thing is flux due to advection. Advection. Okay. Suppose there is a pipe. Okay. We are just going through the definitions right now. Okay. And you are looking at this strip, which has a concentration C at time t, and this length is L, and after some time this has traveled at t plus delta t, and this length is, let us call this as delta L really, delta L. Okay. So I want to find out the, so let us see the mass. So I am writing, let us say I want to find out the flux due to advection. What is the word advection I am using? When there is a flow, okay, then there is advection. Okay. When there is no flow, there is no advection. Okay, is a advection part. So what can I do about write the flux due to advection is concentration times, I can write the volume, so that will become my mass per unit time. So volume will be what? And suppose this area of this thing, the cross sectional area is A, so A times delta L. Okay. Did I get the mass? Okay. And suppose the velocity, if you like to call u. Okay. I can divide this delta t. Is this a flux? mass per unit, or this is not the flux as yet. So what do I do? Multiply by the now do you agree with me, this is flux? Okay. If this is the flux, C times A cancels out, this will be equal to C times U. So this is the one information that we need to remember, because we will be using this information sometimes. So flux due to advection is the mean concentration times the mean speed. Okay. If C is changing with respect to time, okay, things will be different. Then we have to have the derivatives. If U is changing with respect to time, then things will be different. Okay. We have just considered one direction. Okay. So that's why you get, we have to take only the one direction wind, if the directions are different. And the problem with the air pollution, as we'll see, is always three dimensional. Okay. Water pollution you can probably model it with a two dimensional thing. Groundwater flow you can model it with the one dimension, it's just the one dimension going down. Okay. But in air we'll use the three dimension thing. We'll see slowly as we move, we'll like to go to three dimension thing. The next thing which we want to talk about is we'll leave this one there, but we will use it at some point. Okay. So write about the diffusion part. And let's say for simplicity we talk only about the molecular diffusion. Molecular diffusion. You remember the Fick's law? Okay. What I molecular diffusion, what I really mean, if I can give you a simple example. Okay. You have the water filled here, okay, and you have a dropper and you drop ink, let's say. So after some time you see the ink is kind of getting diffused. Okay. So in this case the Fick's law says the diffusion, okay, or the flux, okay, is the J. What name did we give it? A, that was advection. For diffusion, let's call this as G. So that is, and the flux is, with time it is reducing, so that is proportional to minus of concentration gradient. Okay, that's the Fick's law. Okay, so this JD, constant of proportionality, we are just talking one dimension, don't forget about this. And D is called, as you will remember from the earlier classes, something is the molecular diffusivity or diffusion coefficient. Well, molecular is anyway we are talking about is a diffusivity or diffusion coefficient. Okay. And what will be the units of D? Please tell me, because many students forget the units of the D. Quickly derive and so that you are sure about it. Meters per time, meters square per time, meters square, time square. Well, you tell me, I write the number. Length, okay, right, square, time, right, okay, don't forget that, that's Okay, characteristic value of the molecular diffusion, it depends on to the substances which you are talking about. It depends on the medium in which it is getting transported. It depends on to the characteristics or the properties of the substance that is being diffused and things like that. A typical characteristic value in the air, typical for particles and things like, typical value of the D is of the order of let me check the number. Okay, that looks good. Okay. Again, well, you have noted this one down, so I'll remove this. Another simple example. Suppose we, and this value of, let's also define another thing. Characteristic time, okay, for the molecular diffusion, okay, and this was given by Albert Einstein. He said that the typical distance of the diffusion, how far the thing will go, is of the order of 2 times dt. Okay. And again, what we are talking about, don't forget, we are not jumping anywhere else, but we are just talking molecular diffusion right now. Okay. So I just worked out a very hypothetical example. We said, suppose from Delhi a non-reactive pollutant is going and coming to Kanpur. Okay. And the wind speed is, well, wind speed I took this as 5 meters per second, and suppose this wind speed is maintained, okay, and the distance is I took as 400 kilometers, or you can say 400,000 meters, okay. And suppose only the molecular diffusion was taking place, okay, and value of D would take that as 1 into 10 to the power minus 6 centimeter squares per second, or if you want to convert this into the meters, then what will what this value will be? meters per second, and I want to find out what is the characteristic distance the particle will disperse. Okay. So if there was a plume which was going on, okay, how much is the pollutants will disperse from their mean position? Okay, that is what we want to find out. If again a very hypothetical, unrealistic example, but we then want to conclude something at the end of this one. So what do? What I need is a time, so I can find out the time that will be taken for the pollutants to travel from Delhi to Kanpur, and that of course you can do that. I will try to give you the number, and the time came out to be, correct me if I am wrong, as 80,000 seconds, right? Okay, the T was 80,000 seconds, okay, and now I have everything what I need there is that X, the mean dispersion that will take place in the X direction. Of course, we are just assuming one direction. That came out to be 2 times D is your what? And that, since I brought the calculator, I might as well do it. How much? Okay. Somebody said 4 into 10 to the minus 3. Well, we are assuming that to be correct, but this you can correct in case even if it is wrong, doesn't matter. So that is kind of meters, or that will be equal to 4 millimeter, right. Okay. If this was the situation, okay, I think we can't live on this earth, because if the pollutant traveled and then only the mean distance it traveled was only, let's say, 4 mm or something, it means, well, there's something more is happening. Okay. So the molecular diffusion, it gives us the basis, okay, it gives us the argument to develop, but then it is not alone the molecular diffusion that takes place in the atmosphere. So then this theory is fine when you are talking about in a small system where molecular diffusion is only effective, but you will see here the molecular diffusion cannot be effective in this case in our atmosphere. As to the basic thing is U is never fixed, okay, it is always there are the fluctuations. Okay. If I have to plot the U with time, you might have the average velocities like this. Okay. So that U at any time, any instant time is U bar plus, that is the U bar plus the plus or minus or whatever that fluctuations may be in terms of this one. Okay. So that is the situation which is existing. The another thing what we know, so this will create not the steady state condition, this will add to the diffusion part. So diffusion will be much more. The another thing which I can tell you is the wind profile will be like this in the atmosphere. This is your, what do we say, Z, and then what we are plotting this side is a U. Okay. At any instant point we take, the velocity just above that point is different and velocity just below that point is different. Okay. So there is always a shear. Okay. So there will be shear diffusion in addition to what things we are talking about. So shear diffusion or diffusion due to shear, that is a better term. So this, now what we want to say is that one diffusion is because of the turbulence. So this is because of turbulence. If there was no turbulence, then you will get the straight this. So the turbulence and second thing is diffusion. Okay. So if I have the turbulence and diffusion, okay, I might still be can use the Fick's law, okay, because this will still be this thing, but what will change is the D, because D will no more be molecular diffusion in the atmosphere, but it could be a combination of molecular diffusion plus a turbulent diffusion or the diffusion due to shear and things like that. Okay. So that's what we have to consider, that in our next calculation whatever we do, we should say, well, if we really want to find out what will happen to the pollutants when they travel from Delhi to Kanpur, they are not going to disperse just by 4 mm or whatever number that we got, but it will be much more. So let's say we utilize this knowledge. Okay. If you say this D will vary, okay, then this D with your knowledge of last two classes will depend on what? What determines the turbulence in the atmosphere? Mixing height is one thing, and the other thing, mixing height because of the wind pattern. What is that thing which we have spent so much of time understanding and that influences the turbulence? Solar radiation, but then that solar radiation we have measured in what terms? Atmospheric stability. So you say here that D will be function of atmospheric stability. I mean, see, sometimes we want to learn the things not in terms of quantitative, but we should get the feel qualitative. That's what is more concept, to get a qualitative sense of the thing. See, mathematics can be done, mathematics is there in the books and things like that, but then we want to see, well, because this theory is pretty well developed, okay, everyone knows about this one. So the D will be a function of, okay, D will be a function of the atmospheric turbulence. And atmospheric turbulence, as the air pollution person or the meteorologist, we say, okay, the indication or indicator of the turbulence is the atmospheric stability, where we spend so much of time learning the atmospheric stability. Okay, then we want to start something new, but I think the time stops us here. So unless you have a question, we will stop the class here and meet in the next class. Okay. Because I want to derive, I'm sure you must have heard about that will take a little time. So I have to draw some boxes and things like that. So we'll stop it there.